happy to invite one of the PhD students, Hugo, in our department to give a talk today. Let me briefly introduce Hugo before we start. Hugo Rox is a PhD student in robotics at the Department of Electrical Engineering, NTNU. He was born in Toulouse, France, and joined NTNU 3 years ago under the supervision of Professor Jackie Baltes. Hugo has a strong background in software engineering and holds a master's degree in robotics. His research focused on robotics, particularly the application of deep learning to robotic systems. He is currently working on deep reinforcement learning and model-based learning for real-time dynamic systems using transformers for long-term prediction in lab robots and other challenge tasks such as robotic scooters. Okay, so please join me in welcome Hugo.
Hello? Okay. So hello everybody, thanks for having me today. For this seminar presentation we will mostly speak about robotics and especially speak about the robot scooter system that you might have seen already in the campus or just downstairs near the elevator. I'm very sorry for my very thick French accent. I cannot do much about this. And I will try to stay quite general in this talk, but I'm still specialized in robotics, so I'm sorry if some topics are a little bit too specific. You can ask questions in the end, okay? And don't be shy to ask questions. So, as I was introduced, I'm from France, especially from south of France, Toulouse, which is a quite old city and mostly famous for being the Airbus headquarters and the Ariane Group headquarters, which is the European Space Agency. I started my studies by a bachelor in software engineering, where I just learned like object programming, software, the basis basically, database management, websites and all that. And then I did an internship, my first internship in Taiwan, in a company specialized in machine vision for industrial applications. So to find the defects in PCBs and this style of applications. Then I did my master's degree in robotics in France, in Toulouse. And I've done my internship in a defense company in France, where I cannot really talk too much about this, so we will skip to the next one. And I'm now here doing my PhD in Taiwan, and I often get questions like why, because most Taiwanese don't like Taiwan and want to leave. I don't know why. I think Taiwan is a really cool country, really beautiful. The first time I came here, I really liked it, so I wanted to come back. And I found in NTNU Professor Jackie Baltes, which had a very interesting project running, and I wanted to challenge myself because working in a company is very different from doing research. And my thinking at the time was everyone has got to be a master soon. So, like most people know, have a bachelor degree. Most people in few years will have a master degree. PhD may be useful, and I wanted to do research, so that's why I came here basically. So for this specific talk, we will introduce the problem that I choose with Jackie Baltes for my PhD. So we have a robot and a scooter, and basically we would like to pass the Taiwanese scooter license test. That's the basic problem, but obviously you cannot just take your robot and your scooter, put it on the field and hope everything will work. Basically because it's dangerous, of course, and we currently don't have sample efficient enough algorithms to learn on the fly, right? Most machine learning and deep learning algorithms, they need millions of samples, and if you do one run of the Taiwanese test, you as a human will learn, but for a reinforcement learning system, it's not possible yet. So what we do is we simulate the training, and from there we get our million samples. The problem is this leads to major sim-to-real challenges. The first one being not sim-to-real, but real-to-sim, because some robots have a very complex system identification, which is basically how you take the real-life physics of the robot and you put it in the simulation. And the simulation sometimes has limitations, and most simulators are rigid body simulators nowadays, so meaning you cannot have soft materials, but if you did a little bit of physics, you know that everything is soft, even metal is soft, okay? And we will see later that the Gogoro scooter is especially very soft, even the frame of the scooter. And then, even if you have a good simulation, you still can have problems in sim-to-real, and you can have bad training, basically, because you need to tune your reward function. So our goal was to check if we could do it, if the current tools would be sufficient, what problems we will face, and how to solve them, okay? That was the basic PhD target for the first year. And the motivation is that even though you see a lot of videos of robots working and working nowadays, because companies invest a lot and they do a lot of YouTube propaganda, especially in China, the real thing is it's still quite hard, and a minor failure in the system will lead to catastrophic results, and sometimes it can be a little bit funny. But even big companies like Boston Dynamics, the backflips, they cannot do it 100% of the times. It's not so good nowadays. It's getting better and better, but we are still not there. So what we will do is just train a model with the methods that they use in most of the robotics companies, which is PPO. Then we will test the modern sim-to-real approach, which is using domain randomization. And then we will observe what we can do. And as I said, soft body physics is a big problem for us. We will talk a little bit more about domain randomization later. If you don't know what it is, we will go deeply there. And of course, for a more general topic, this is more for the thesis committee. But you can say the scooter robots is a cool project because of last mile delivery, and it's the main transportation in Southeast Asia. The real thing is we will never have this in the next 10 years. I'm not very confident that scooters will be driven by robots in the near future, because I've seen my robot. It's not the best one, but I don't think the government will allow anything like that. So another motivation is just, you see a lot of cool stuff on YouTube, right? You see robot boxing, robots walking on their hands, doing backflips, and solving interesting challenges is quite important. It's always interesting, and that's a big point of Professor Bartes. He really likes this kind of challenges. He really likes to push the current envelope of what we can do, because we don't really know what this will allow us to do in the future. That's part of research. You don't really know what you will find, right? In the related work, we have quite a lot of stuff. We have the Yamaha Motorbot and the Robotics and AI Institute, UMV, which both are not really humanoid robots. They are custom-built machines that are bolted on a motorcycle or on a BMX. So they are kind of out of the scope of the PhD, but they are still interesting because they are able to control the motorcycle at very high speed and a BMX at quite low speed. These two didn't exist when I started my PhD, so to tell you like how fast the robotics scene is moving recently. Then we have AGBot X2, which is much closer to what I'm trying to do, which is quite a huge company, and of course it's a bike, it's different, but it's still very close to what I'm trying to do. The thing is, they didn't publish anything about this. It's like a 3-second segment on a YouTube video, so it's a little bit hard to tell how they did. I guess they used PPO like everybody is doing right now, but hard to guess. And then we have this little guy, which you might have already seen if you are in the robotics scene, is Dr. Gero, which is a Japanese researcher. Very, very good guy. The problem with this is that he is Japanese and he doesn't publish any paper in the English scene, so I cannot read his papers. And it's very hard to find his papers. But it's very, very good, but it's a very small size humanoid robot, but I really recommend to watch his videos. But again, it's not a scooter. So we have a gap in the research, and we would like to just solve this gap, solve this problem. Because scooters and bikes are quite different, as you know. One is very heavy, which means the inertia is very high, which means if you try to turn and you make a mistake, one mistake is fatal because your controller needs to react very quickly, right? If you make a driving mistake and you are too slow to realize, then you will fall much harder to control. Also, the center of gravity is much lower, which makes the problem harder in the physical aspect, right? If you know the inverted pendulum, the higher the length, the harder, the easier. So, yeah, we have a very small region of attraction when we do our system identification. But even though it's interesting, this is not the real end product of my PhD. This is just a cool side project. The end project will be to, as we will see later, improve how Sim2Real works and improve, like, come up with new methods to do Sim2Real. So we propose a benchmark for our program because we are the first ones, so we need to put some benchmarks. The first part is to complete the full 150 meters line that we have just in front of the door here. We are in this building. And then do a full turn of the campus, left and right. And then we have a new challenge, which is to complete the first part of the Taiwanese scooter license test. For now, I don't aim to do the full license because I don't want to graduate in 10 years. So let's just focus on the first part. I think everybody knows that what is the challenge. You have a 15-meter line, 40 to 30 centimeter, and you have to do it in more than 7 seconds. The robot we have is the Torment 3 humanoid robot. We have upgraded it a little bit with a new PC, actually 2 new PCs. We also have installed the Intel T265, which is a stereo camera that allows us to do SLAM, so we can localize ourselves, hopefully better in the near future, but that's the work for our master degrees. And we have a new IMU because we broke the old one, and this is quite expensive, and that's the problem in robotics, is like you have to work with hardware and software And a lot of times the hardware doesn't want to work and it breaks very easily. We are outside doing testing. The outside world is terrible for robots, especially in Taiwan, where the humidity is always like 80%, and in Taipei it's always raining. I don't know why. So that's a huge problem for us. We decided to not put any sensors on the scooter. Why? Because we want to keep the task as close as just a human would do, right? You don't plug yourself to the scooter when you drive. So we just want to have the humanoid robot jump on the scooter and drive, okay? To keep it interesting. Otherwise, we fall back to the first robots that I show you, like the Yamaha robot. That's cool, but that's not what we want. Another big problem that we have is the robot cannot roll. And this is pretty interesting, because when you drive a scooter, you usually tilt a little bit your body in the turns, right? Maybe you don't feel it, but you do it, and that's helping you a lot to switch your center of gravity position, and the robot cannot do it. So the robot can only rely on the steering part. So it needs to do some tricks to get the balance right. We have spent a lot of time, actually the whole first year, just doing safety protocols around the robot. So we've installed a new frame on the robot, which really attaches the robot on the scooter. So, because the robot is very expensive, so if it falls, Jackie won't be happy. So we've attached it to the scooter frame. We also have I added some wheels so it doesn't fall. The wheels are not touching the ground, okay? They are a little bit up compared to the other wheels. That's crazy, but some reviewers didn't understand that. Then we have here, maybe it's hard to say, but we have a huge servo motors with like 300 kg per centimeter of force, so it will pull the brake very, very strongly. This is connected to a remote control switch, which is just a basic Arduino with a 2.4 gigahertz like digital wire. So like if this battery cuts, or if the user click on the button, or if the user click on this button, or if it falls, the scooter will stop, okay? So this is like a dead switch that we use for experiments, just in case, because we don't want the robot to just throttle the scooter and fly away, and then we cannot follow him. And this is powered by an independent power supply, independent from the scooter and from the robot. So we try to keep the safety very high. And we also have added some speed limitation. So this is kind of hacking the Gogoro scooter. Gogoro is very angry if you touch at their MCU. They are like Apple of the scooter world. They don't like you to modify the scooter. They don't give the source code. They don't give anything. So I had to like do some hacking of the robot to make it work. So you have a button that controls the motor power. So if you touch this button, the power of the scooter will turn off. And here I have a small potentiometer that controls the maximum speed of the scooter. So this is very important because the robot can turn the handle of the scooter, and this can actually stop the maximum speed to maybe like 10 kilometers per hour. This was found by another student, not me. I just made it a little bit thinner, but it was done by a master's degree. And so let's present the software stack that we use. We have the robot, okay. We have a sensor that just collect all the sensors information. So we have the camera, the IMU, the joint position. We have a lot of sensors. Then we filter this data, send it to the control node. and then the control node send it to the inverse kinematic mode, which then give the motor position for the robot, and this loop have to run at around 100 Hz. So it's quite a lot to run, especially the IK node. So we had to do everything in C++, no Python in the robot. And why don't we do direct joint control, which is very popular nowadays because most robotics company will do torque control or direct joint controls. But you see, the control node output the target steering, and then the IK node choose the motor positions. But it's very possible to just here in the control node output the motor position, because your neural network can output the joint position of your robot. It can control your robot. We choose to do that because we didn't want the robot to be too free. So the robot is limited in his range of movement. The robot cannot leave the handles of the scooter and hurt somebody. It cannot do that. If you do direct joint control, the robot can. And we saw in the little funny videos that the robot can really, like if you have a sensor fault, it can really be dangerous. So imagine this, but on a scooter, it's not ideal. So to do that, we had to engineer a new IK stack, which is not so easy to understand, so I will be a little bit quick on that. So you have the frame of the robot, right? So the frame of the robot is on the, basically in the pelvis of the robot. And then you have the steering frame. The problem is to steer the robot properly, you have to know where is the steering, right? You have to know where to put your hands. And for this you can maybe use machine vision. We didn't do that. What we did is, before starting the robot, we collect some data points. So we screw the hands on the handles, right? We collect some data points, the blue and red points, okay? Sometimes maybe you see me outside, turn the robot by hand. That's what I'm doing. So then we can basically find where is the steering axis compared to the robot frame. So we are looking for the transformation from the origin to the steering frame, right? We collect our points. We can fit a plane in this set of points, right? Very simple. We can get the rotation matrix from this plane. And then we can fit two spheres with this data point, right? And the two spheres condition is they have the same center. And then we can get the translation matrix and the rotating radius of the two spheres. And then now we have the trajectory of the hands. That took a while to do that because it's very important for us to not overtalk the robot. The robot can basically take the scooter and lift it. It's very powerful. So if we didn't do that, we will break the motor hands because they are connected physically to the handles. And then we just, this is 10, not 100. And we just optimize using the central difference method to run this IK using the joint works, the joint position. That's very basic, nothing very interesting. Now we are going to talk about more interesting stuff. So we had a previous work with a very good student, Chrisman, and he did a lot of simulation, and the results in simulation were quite good, a little bit too good, because the scooter cannot really do that. So the simulation was a little bit unrealistic compared to the real life. What we had in real life could really not lean like that and keep control. And especially we did not have enough speed, like we kept our speed under 10 km/h to do this kind of things. Okay, So we have a simulation environment which is Isaac Gym, which is a little bit old now, which allows us to use parallel environments, which turns on the GPU and allows us to do very fast deep reinforcement learning and very easy domain randomization. We will talk about it a little bit later. So we run like 4,000 simulation on one GPU. The problem, as I said, is we have rigid body physics, and the robot is not rigid, the scooter is not rigid, the wheel of the scooters are not rigid, so that makes everything quite hard to do sim-to-real. We also cannot do closed loop control, so maybe you can see, but in the simulation, the scooter doesn't touch the robot, so like he's driving without touching the handles, which makes it even more unrealistic. And of course, we enjoy our friend from NVIDIA, which makes terrible drivers, and Isaac Gym and Isaac Lab are terrible to install. Anyway, so to do sim-to-real, you first have to do real-to-sim, which is taking your robot and putting it in the simulation as the best as you can. You really have to spend a lot of time doing that, otherwise you will train on garbage. And as we say always, is garbage in, garbage out, okay? So the scooter looks like this, right? And we give it a target steering angle. Then the IK find how to move the hands of the scooter to match this angle. Okay? But how fast does it do that? And can we simulate how our real-life C++ IK works? Because the inverse kinematic optimization is not linear, right? It will depend how close is your target, how good is your CPU. It depends on a lot of things. If your CPU is doing something else, it's not very stable. The time to move is not stable. So what we do to system identification is very interesting. You should listen to this if you have problems with tuning PIDs in your simulations. That's a big problem that we had, because the PID of just this joint in the simulation is one motor. In real life, it's 14 motors. So that's making the problem even more difficult. But the original problem that most people face is you have a real life motor, and the company that gave you the motor have a little bit of a random specification in the data sheet. And NVIDIA also have a very random way to set up the PID numbers in their simulation. So what we do is we send a chirp signal to the scooter and to the simulation, okay? So the chirp signal is the target steering. And then we collect the results, like the current steering, so from the simulation in green and in red, and from the real-life scooter in green. And then this allows us to fine-tune the damping and stiffness of the motors, because the chirp signal is, as if you don't know, it's a signal with varying frequency, right? Sine wave with varying frequency. So then we can see, we give the same signal in input, and we have two different signals in output, okay? And then we can tune our simulation PID gains to basically get the closest signal as possible, right? And this is how we tuned it, and I believe this can be used even if you only do one motor. The problem is, this is not a differentiable problem, because your simulation is not differentiable. In most of simulators are not differentiable. So what you can do is run genetic algorithms to find the optimal PID gains, right? Or if you're lazy like me, you can just plot everything and just find it in the picture. It's much easier. And this way you can see if you use this kind of like high damping and low stiffness, you have very high error, and if you use something around this line, you have a quite good PID compared to the real life response. And here you can see the real life data. So in orange the simulation, and in green the real life. And you can see this is after tuning, so it's very close to real life. But when we are around, I don't know, around like 15 radians per second in frequency, we see that it's totally losing the tracking of the real life system. Why is that? You can see the simulation is perfect, because simulations are always perfect, but the real life robot after 15 radians per second just gave up. And because the frequency at which you control your motor sometimes cannot be done by the motors, right? So in our test, when we ask the robot to steer faster, faster, faster and faster, at one point the robot just cannot steer faster and will execute random commands. That's, even if you only have one motor, if you give very high frequency control commands, like left, right, left, right, left, right, at one point it will stop to follow your commands, right? It will be stuck on the left, on the right, or somewhere in the middle and oscillate. That's what's happening. And that's interesting because it tells you again, even if you do the best you can to do system identification, you will have problems with sim2real because some simulations are just too perfect for now. So then we have domain randomization, which we will specify a little bit later, but basically you add noise to your sensor data. So for the sensor data, most of the data comes from the IMU. Some data comes from a remote control because the robot doesn't decide where it's going. I'm controlling it, okay? Now the project is only focused on how to not fall and how to follow the command. We don't have a navigation part for now. So the robot is just following my commands. So you need a remote. And then we use the Intel 265 for forward velocity. It's terrible, it's very noisy, and hopefully our master students will be able to make it work better. And so that's our system, that's our sensors. And we add a lot of noise to the inputs. We usually, what I'm doing is I just check the data sheet and I do double what the data sheet tells because they are all very precise and all the tests in like laboratories, but outside when the sun in Taiwan is like 40 degrees, the sensors tend to not be so accurate. Then what we do is in the simulation we switch a little bit the scooter, the robot, sitting position because in real life we also never sit the scooter in the same way. That's one other thing that is interesting about the project is we really want the robot to just sit on the scooter and we don't want to have very precise alignment with the scooter. But of course that's making the problem harder because then your center of mass is not aligned with your wheels, which is a little bit boring. We add random pushes in the simulation, so you push the head of the robot and you train him to not fall. And we have purling ground, which for some reason takes like 50% of the GPU resources. Then we use PPO as a baseline to check our future algorithms. So it's not super interesting, that's just the PPO parameters. Why PPO? Because the implementations are already done, it's really easy to use. It's quite stable even if you have bad hyperparameters. and we just have a very easy reward function, which is basically don't lean too much, follow the command, don't move the steering too much, and don't move the steering too much again. And we have a symmetry loss, which we will see a little bit later. This is not super interesting, it's more technical. Then we have our training curve, also not very interesting. We can see it's learning quite quickly, but to really make it better and able to run in real life, we still have to wait for about 2 days of simulation, which is quite long if you want to change some reward functions. So the full stack looks a little bit like this. We have the IMU, the camera, and the remote. All of this data is aggregated together, sent to our neural network. We have a little trick here that I'm going to talk just the next slide. Then the model gives us target steering. The remote also gives the target throttle. I didn't talk about this, but the neural network doesn't control the throttle. This is again a safety measure because we don't want the neural network to just fly away with the scooter. We want to control the speed using the remote. Then all that is sent to the inverse kinematics, and this is sent to the robot. All of this is in C++, and this just calls a ROS node. So we have some results now. I don't know which one, maybe this. We have maybe 2 weeks ago successfully passed the Taiwanese scooter license test. It's a little bit hard to see, but there is 2 lines on the ground, and maybe, yeah. Yeah, and the robot is able to pass the test actually in around 10 seconds, which is really slow, which also makes the problem even harder. The slower you go, the harder it is, right? So that was quite an achievement, and we were happy about this. Okay. Sorry, I have no idea how to go back to the normal presentation. Anyway, it's okay. Then we also are able to run the robot without retraining with me on the robot. So the robot is able to carry people. So I'm not driving, I'm just holding the robot, right? You can see I'm just seated on the robot. It's also able to like take the bumpers, you can see, which is quite interesting because this is not in our simulation, right? This is just the part of domain randomization that allows us to do that. And yeah, I don't know, just some free driving in the campus. You can still see that the robot is doing a lot of commands, right? It's very, very slow, and the ground is not super flat in the campus. I have a lot of like bumps and gravel. But yeah, the results are pretty nice, and we were quite happy with that. But they were quite hard to get for multiple reasons. But maybe now I can give some tips for reinforcement learning. Just let me try to reload so I can go back to full screen. Okay. Okay. So the first tip I will give is that you see in machine like deep learning, especially for image, people use data augmentation a lot. and that's really helpful. Like you can make your dataset 10 times bigger. We can do that in reinforcement learning, and I don't know why nobody does that. But for example, any physical system that we have axial symmetry. So if you do humanoid robots walking, they are symmetric, right? My meaning is that if you have your state space, okay, and you just reverse the number. So if you're falling this way and you take a symmetry of this, it's the same, right? So you can just double the efficiency of your training just by using symmetry. That's a very interesting tip that if you don't have a big GPU, I really recommend. Another thing is we rely a lot on Markov process, which is like you can basically predict the next state depending on the current one, right? But it doesn't mean it's easy, and it doesn't mean that your neural network will be able to do it. So right now you can see the trend, and it's very easy to say like, okay, it's more or less gonna go up this way, right? But if I give you just the last state, it's very, very hard for you to make a prediction on how the trend is evolving. And right now it was backwards, right? The thing is, most people, when they train reinforcement learning agents, they only give the last state to the model, okay? But you can just give a state history instead of just using the last state. This is quite common, and this improves the performance a lot of the system. Because now, instead of having a very noisy data, the algorithm can just, the model can just learn how to filter this data. So it's very, very interesting. Another tip would be very careful with domain randomization. And we will talk, now is the time to talk a little bit more about domain randomization. So you have a robot, okay? This is your real life robot. And as we saw, you have a simulation, and the simulation is usually a little bit different from the real robot, okay? So in this slide, I made the robot a little bit shorter and a little bit wider, okay? And the thing is, you can actually change the simulation to encompass more and more different type of robots. So you can make your robot much wider, you can make it much smaller and wider, you can just make it much smaller. And this is what we call domain randomization. And that's why parallel environments are very useful, is because you can train your model, okay, to use all of this, to learn how to work with all these different bodies in the same time, right? So after training with domain randomization, you will have a controller that is able to work with this body, work with this body, work with everybody. And if your domain randomization is large enough, then it's also englobing this robot, the real robot, okay? And you don't really care about working with a big robot and all, but the thing is, you don't really know the dynamics, because if you knew the simulation and the robot dynamics would be the same, right? But you don't know, so you just make the simulation domain a little bit larger and you train on that. The problem is that this is challenging, because if you learn to work with different bodies, if your bodies are too different, it becomes very hard to learn to work. And now your controller doesn't just have to learn how to control a working robot, it also has to learn how to control every possible body and balance every possible body, and that's not easy. So what you can do is just give the actual parameters of your simulation to your neural network. And that's a very simple trick, and that does change your problem to, I want a controller that works for every robot, to a controller that works for a given robot. Why? Because the neural network knows what robot he's controlling now, okay? And that makes the domain randomization much easier to learn, because before he was blind, he didn't know what body type he was, but now you tell him. So I'm choosing body type now, but if you're randomizing, for example, the motor's torque, you can just tell the controller, oh no, for this robot you are using this torque, okay? And now you have a model that you are able to tune in real life, okay? Because these numbers are still here, even in real life, okay? And the interesting part is that you can do the sim to real approach, and you can change these parameters in real life and try to match your real model, which is very useful, because if you didn't do that, you will have to do retraining every time you wanted to try something new. So be careful with domain randomization, because it's making the robot, the model job much harder. So if you have a too huge domain, then it's harder to train, and the quality of your training, will degrade. So now we will switch to the second part of my PhD. So we talked a little bit about PPO. I didn't present the algorithm. We don't really care about this today. I'm sure some people know about it. It's just a reinforcement learning algorithm. It's very easy to parallelize. It's a very smart algorithm from John, which he's a very, very good researcher. If you don't know him, you should check his work. He's a guy from Berkeley. He did TRPO, PPO. He's the co-founder of ChatGPT. His chief scientists are at Claude AI. I know he made his own company. So if you don't know where to invest, I think this guy is a good bet. And the problem with PPO is that it's pretty old now. If you're doing research and you see companies publishing YouTube video about stuff that you're doing, you're not doing real research, you are just following the trend, right? So the humanoid robot walking, every company knows how to do this. It's not research anymore, it's just implementation now. And PPO is in this kind of fields, right? It's cool. You can think, wow, it's driving, it's interesting, but to me it's not research, it's just basic engineering. Any master's degree can do that. Another problem with PPO, as we said, is the quality of your policy depends on the simulation, right? That's a big problem, because you cannot use real-life data to train your PPO algorithm. You can do this in Softactor Critic, but you cannot in PPO. You need to retrain every time you want to solve a new task. So if you want to train the walking, you train your walking. Then you want to do a backflip, you have to retrain. And everybody that did reinforcement learning knows that it's quite easy to retrain, but finding the proper reward function is very boring. So it's not so good at like switching tasks. And also it's a reflex-based controller, which doesn't have any planning compared to older approaches like the NPC, for example, is just giving the next action, which is okay for some tasks, but if you have a long task, like a long planning task, like solving a maze or this kind of tasks, that can be a limiting factor. So another limiting factor that we have, and I told you, I told you in the beginning that everything is soft, and I don't know if it's easy to see in this video, but you can see when the robot is turning, the robot body is moving compared to the scooter frame. Okay, so you can see there is a lot of vibration and a lot of movement in the scooter frame. This is the velocity of the angular velocity of the scooter base, and the problem with that is like even if the robot is not moving at all, if I give this data to my PPO controller, okay, this data will tell my PPO controller, oh, I'm falling, because it's registering that the angular velocity is going down, going up. And we have another big problem is that I don't know how Gogoro make their scooters, but you can see that the robot is able to completely bend the frame of the scooter. It's a little bit subtle, but I'm not very strong. I can bend the Gogoro scooter in two, okay? And I'm not a big guy, so I don't know. There is like two metal tubes here, but you can see the steering angle is still bending. So that's a huge problem, because in the beginning I told you, oh, we are trying to find where is the steering axis, right? And now I tell you, oh, the steering axis, it's kind of random. It's like maybe in 5 centimeters this way, or maybe not. So yeah, thank you, Gogoro. So you can see all this kind of noise depends on the steering, right? And there is a relationship in the green. The green is the steering angle, okay? And you can see when there is a big spike in steering, there is also always a big spike in the angular velocity. Even though this is data from the scooter that is not moving, okay? It's fixed on the ground, so it should be quite flat here. So we have a big problem here, because the scooter will just think, oh, I'm falling, so I will turn right. And oh, I'm falling the other way, because now I turn right, so I will turn left. And then the robot is driving like a snake. He will just like turn and turn and turn and turn and overcorrect. I kind of in airplanes like the driver induced oscillations. And why we have this problem, as I said, is because everything is soft. The seat is soft, the wheels are soft, the damping is soft, the scooter is soft. But the problem is we don't have the simulation power to simulate this. We could have it, right, if we had a supercomputer or something, but that's not the point. And most of these kind of simulations are only for deformation. They don't do like real-time physics. So it's possible, but that's our goal was to find a way to go around it, right? So what we can do is, instead of giving the simulation to the policy and just learn how to control in a simulation, we can use something that is called the world model. So we take the current states and the future action that we want to take. We give it to our world model, which is a neural network, okay? And the neural network learns how to predict the future of the simulation, okay? It's very basic. It's just you have a state, you have the action that you want to take, and then the model just predicts where this action will lead, okay? And this is batch, so I can just have just like PPO, I can have like 4,000 scooters going and 4,000 predictions, and it's differentiable, so I can run NPC style control on this. So if you're doing a little bit of automation, you can think of this as the differentiable equation for your system, right? And what we can do is just train an actor using the world model, or we can do NPC style optimization. And you might think, okay, training an actor and a world model, not so interesting, but this is the idea between Dreamer v3, okay, which was the first reinforcement learning algorithm to find diamonds in Minecraft, which is a very big deal, because it's actually they kind of cheat a bit, but anyway, it's very, very long-term planning, right? So that's very interesting. And you can just do a simple optimization, and here you can use a lot of different techniques. It's very old, it's older than me. So the thing is, in this kind of optimizations, the planning maybe on a window of like 10 seconds, and it's very, very hard to plan for very long-term horizons. And you might think, okay, it's still kind of useless because I have my environments, my world model, and my future states. So my world model will just learn how the simulation works. So I still rely on how good is the simulation to do my control, right? But actually, you can use real data too. You can collect data from real life, and you can feed them to the world model and ask your world model, okay, can you predict the future of this data? And because you can do that, and you have the real life results, what you can do is pre-train on the simulation, right? So the basic physics of how driving a scooter, how a walking robot works is understood by the world model. And then you can fine-tune it with real data, and then you don't need to do system identification. You don't need all the things I was talking about in the beginning, like the PID controllers and everything, because your model can just learn it directly from real-life data. Because in this data, there is physics. The next step depends on the previous steps, and it depends on how the physical worlds behave. So the world model is able to learn how physics works, and that's pretty interesting. The problem is, of course, the high quality data from real life is quite sparse, right? You cannot, I mean, we could collect a lot of data, but that takes a lot of time. And we have a lot of low quality data from simulations, so we can just pre-train with this and then fine-tune with this. Or we can mix, we can do a lot of different stuff with the data. We've tried this already. For this, we use transformers because they are pretty good at predicting sequences of data, right? So what we are doing is we give a small sample of the past, so the last 5 steps that the scooter took, and then we try to predict the next steps, like the 30 next steps, I think, in this example. Maybe more, I don't remember. So you can see also that real data is quite noisy and it's a little bit harder to predict than simulation, but we still are able to predict it more or less accurately, and we still are able to predict it well enough to control our scooter. So yeah, and this works with every single observation that we have. So it's quite interesting. This is not so interesting. Okay, so this is the overview. So we just give the current state. The transformer find the next states, like the next 30 states. It depends how you configure it. Then we have our objective function, and we train a policy to find the actions. And the thing is, all of this is differentiable now. Okay, so you can just directly train your policy from the action he took, because it's not really using the simulation anymore. It's simulating itself in its head, right? So it's differentiable, and the gradients are very easy to compute because it's just a transformer, right? You can use a critic instead of an objective function, but we don't do that. The problem is this will very easily lead to unstable training and an exploration-exploitation problem that is very common in reinforcement learning, so that's not a very good approach. Sorry. What we can do is simply use, instead of policy, like instead of another neural network to find the actions, we can use an optimizer. So I give one action and it gives one possible result, right? And if I give like n actions, it will generate n predictions. If the actions are the same, of course, it will generate the same prediction. And now if you see this and you're like, oh, it's useless. And not really. You can do genetic algorithms on this. You can do a lot of different parallel optimization on this, because you just have to shoot random actions in the input, and then you choose the one that generates the future that you want, right? That's very simple. And the problem is that this is very multimodal, and this kind of problem is hard for regression optimizers. We can use particle swarm optimization for this, but it's not very good for like super high speed control. So we have a problem of a slow controller. We could use quadratic programming, like MPC style methods and interior points methods. The problem is the gradients of the transformers are a little bit slow to compute. So you might know that most Python libraries now implement something that they call the fast transformer, but the problem is the fast transformer is only fast in one way, in the inference way. In the backward propagation, it's not so fast. So that's a big problem for us. Like going this way in the transformer is very slow. So what we can do is, instead of learning the forward dynamic model, we can learn the backward dynamic model. So this is what we do now. We have a state, we train it to predict the next state, and we already know the next state, so we can do basic optimization to change the weight. And then when we use it, we have the target state, and we optimize the action, so the output state match the target state. That's very simple, that's just MPC control. Now what we can do is, instead of doing this, we flip it, okay? We take this and we put it as an input. So now you have a model that is trying to predict what action I took from state 1 to state 2, okay? And that's an interesting thing to try, because then you have a controller that you can use without any optimizer, but you still can change the targets at runtime, which is totally different from PPO, which you need to retrain. This controller doesn't need to retrain. It will be zero shot in any task of your robot, giving, of course, enough training for the world model. But if the world model understands the physics of your robot, you can ask him to walk, you can ask him to jump, you can ask him to do a backflip, it will do it, you don't need any retraining. So that's a very interesting power for this kind of models. So you just have to change the target states, and there is no optimization, so it's just a forward pass in a transformer, which is very fast nowadays. Yeah. And the final architecture that we have, I don't know why there is a fork anyway. The final architecture that we have is a double transformer architecture. Why? Because we still actually need the forward dynamic model to avoid the backward dynamic to generate always the same action. So this look in the future and check if the action I took in the future makes sense, okay? And this part just tries to, from the current observation that we have, find a set of actions that lead to there, okay? And this can be configured to run around 500 steps in the future. That's where we are doing, that's what we are doing right now. You can do more, you can do less. For the scooter project, 5 seconds, it's about 5 seconds in the future, so that's good enough for driving. And this model is fully supervised, so it's very easy to train. It's doing multi-step planning, which PPO cannot do. And it's zero shot by design, meaning that you can change the future observation that you want and the model should be able to find which actions leads to this observation. In practice, of course, it's a little bit harder and you need a forward dynamic model, but that's the second paper I'm working on right now. And of course, this is a work in progress, but we can see it's able to drive the scooter quite well in simulation, and now I have to do it in real life, which should be not too hard because it's just putting the neural network on the robot. Right now we use Python, so we have to switch to C++, and we have to check if it works better. And yeah, that's about it for me. So the contribution of this PhD would be the first one, fast IK solver for Tormain. Not so interesting. Humanoid benchmark for the scooter, also not so interesting. The first humanoid robot driving a scooter, that's kind of cool for us because it's in NTNU, the first one is nice. And we are working on easier sim-to-real deployment using world models right now. So I hope I will be able to publish this paper soon. So yeah, I finished my talk. If you have any questions, please ask me.
Okay, I think we just take several questions. Any questions? Yes, please.
Thanks. Hi, Hugo. Thanks for the very impressive work. I was a former of Professor Jackie's student, so I was thinking this project is impossible, but I think it's really speechless in terms of very positive way that I want to comment, but also another simple question that I want to ask for your observation, that you mentioned that there is a forward velocity from the Orb SLAM V3. Do you also train that on the simulation, or you just use the ground truth of the linear velocity data from ISAC-G?
The simulation also have the forward velocity, yes, and it's from the base, the root state of the robot in simulation. But the thing is, OrbSLAM is really not so good outside, right? And so the noise is super high in simulation. So I add a lot of noise in simulation. So the noise is 1 meter per second random. So it's very, very high. And yeah, that's a good question, and that's quite important for us to drive, because the speed is a defining factor in the physics of the scooter. Yeah.
Okay. Because I also tested some of this linear velocity problem in the quadruped robot in our company. So I think OrbSLAM will be like one way to solve this. I just have some idea to share with everyone or with you, that we could also use like the data, the proper scientific information from the robot, and then we can make some MLP estimator, like self-supervised learning. So yeah,
that's quite a good idea, and I think our colleague from the Czech Republic also do that with their quadruped robot. The thing is, for the scooter, we don't have the joint. I mean, the joint is not touching the ground, so we cannot do that. But for humanoid, yeah, it's a good idea, I think.
Yeah, thank you. Thank you for your very impressive work.
Thank you.
Any questions?
Come on, it's time for revenge. I know I asked a lot of questions to you guys.
I think after listening to Hugo's presentation, that you, have some sort of idea that this kind of research is highly interdisciplinary. So you integrate a lot of technique. So I think any of the sub-project can be a focus for a master degree or a PhD degree. So yeah, it's amazing. So I'd like to ask on behalf of students some of questions. The first project is model-based. So you do the system identification, based on which you do the simulation and also the realization.
Yeah.
Is that correct? The second one is the so-called world model-based control.
Mm-hmm.
So you basically use deep learning transformer to,
Yeah.
to do this job?
Yeah.
Oh,
we
okay,
use
I see.
transformers.
Okay, that's quite interesting because system identification alone will take some time.
It's very boring. Yeah.
For those who have not yet taken the course called system identification, try it. So that is a very tough subject for those who major in control engineering.
I really recommend control engineering. It's very, very interesting.
Okay. So about the circuit design, you still have to design some circuit. For example, to integrate some MCU circuits to control the system by yourself.
The robot is bought from Korea, so I didn't have to really do anything. The thing is, a year ago I crashed the scooter on the wall of the university. So the IMU was dead, and recently the robot took fire in our lab, so I had to change the circuit board also. But that's not like super high level. Like I know a lot of students are really good at this. I'm not good at like hardware. This part is hard.
I think I better leave the opportunity to students might be able to be interested in asking questions. Any questions from the students? Okay. You are using PPO.
Yeah.
Okay, so I'm still thinking because some of the students who took the course of evolutionary computation. So have you ever done the function optimization by comparing the result by using PPO and some evolutionary algorithm?
The problem with first, the professor doing this class is amazing. You should take this class. But the thing is, the problem with genetic algorithms is they are super slow. So we are running 100 Hz controller, and we really cannot. Like I didn't even try. I know it will be too slow.
Okay.
Yeah.
Okay.
But we use still genetic algorithm to solve some tasks like the system identification part. Yeah.
Before we go, because now you are in the lab doing research about humanoid robots, I was constantly asked the future development of humanoid robots. So can you give your comments?
That's very hard.
The question, let me repeat, because when I go outside to attend meeting, so many people ask me this kind of a question because they sort of two conflict opinion about the future development of humanoid robots. Okay, particularly Elon Musk and also some other big companies are focusing the development of humanoid robot. Your comments.
I think that's hard. Like that's my opinion, right? I might be wrong. I might be right, but that's just an opinion. I don't. I think right now the future of humanoid robotics is not really in robotics. It will be mostly in the fields of like computer science. I've talked about John, which does amazing research. We have seen a lot of advancement in like foundational models and like transformers and this kind of stuff. I think robots, like the hardware part, is basically solved right now. We just have like motors and they work right most of the time. And now we need to focus on how to get more sample efficiency out of our algorithms. Because we would like to have robots that are able to learn by themselves in real life, not in simulation. Because right now, you have to train your robot to do the task. And if the robot see a new task, like if my human robot driving a scooter, I tell him, can you grab this bottle? Impossible. I need 3 more months of coding. So that's the thing. It's cool if you already have a trained model. And we are going to do this with foundational models right now, but yeah, I think it's still quite limited. So I'm average. I don't think I'm good enough to make anything advanced in the field. So I hope better people can make it work. Yeah.
Okay, the reason I ask this question is there is a big company called Dami. Dami is a robotic company, collaborative robotics company, which just IPO on the market. So the boast of the company mentioned that, well, we are not in a stage to realize the benefits of humanoid robots. Instead, he mentioned that we better focus on some wheel or collaborative robotics, which can be easily applicable to the industry. He just mentioned that humanoid robot, but there's still a long way for practical application in the future. So that's the reason I ask these questions. So, in your opinion, so in comparison to, for example, leg robots, wheel robots, collaborative robotics, so what do you think about the perspective, the future of humanoid robots?
I think it's, of course, hard to tell, but I believe, yeah, it's a long way to come, and I think the progress like this last 5 years is really, really huge, and it's showing that we can do it. Like 5 years ago, a walking robot was hard. Now it's super easy. Like any master can do this. Okay, so the progress is immense. I think if you talk about like investing, I think it's a good time because nobody knows too much about it, and yeah, I think it's a promising future in my eyes, but maybe I'm wrong.
Okay. Let me clarify a little bit. 我刚问这个问题，就是因为达米机器人那么最近上市嘛，那个大家应该很清楚。那么就是两派了那广达的那个老板林百里他就觉得说，哇，这个还很遥远但是有一派的人Elon Musk 还有很多公司认为说这是一个必然的发展趋势所以说这个好像看起来有点两极了所以我刚才就问这个问题Okay, so any questions from the students? We can take one or more questions. Okay, good.
So follow up the question by Professor Shi. I want to ask, like, how do humanoid robots can make profit?
For me, there is multiple ways, right? It's like in the gold rush in America, you can be the one searching for gold, or you can be the one that sells the shovel to dig, right? So a lot of companies make humanoid profit by just making the robots and selling it. And like Unitree, for example, is I think the top one right now, and they are doing that. They are investing in the manufacturing part. They are super good at manufacturing, and I think there will have some other companies, and right now like BMW is doing that will use the robots to replace human in factory lines, because right now the robot costs are really going down. Like Unitree can produce a humanoid robot for around like 6,000 USD, which is incredibly low, right? You cost much more to a company than 6,000 USD. So I think a lot of manufacturing job can be optimized this way. And then there is the debate, like, should we do this? And people can lose their job, and maybe it's not so good, right? But many people in the field of philosophy will argue that in the a little bit distant future, if you replace everybody with robots, then you need to rethink your economy, you need to rethink how the resources are shared, right? So that's a really big topic that a lot of people think about. Yeah, but if you just want to make money, I don't know. I cannot give investment. It's not my field. Okay.
Any questions? If there are no further questions, let's give a big applause. Hugo.
Thank you very much.
Thank you.